Good day, everybody. Today we're going to find the gravitational pull certain objects give and vary their shape, see how that affects things, and we will use triple integrals to find the pull. So to start, some preliminaries. Hopefully we know Newton's law of gravity, G(m)(m) over r squared. That's good for spherical objects. If I put it in Cartesian, it looks like that. So that's the magnitude of the force. Now I'm going to put a little point mass at the origin, and I want to find the pull from a mass m that's somewhere else in 3 space. Say it's at xyz. So the direction of the pull is from m towards big M, or this would be the direction as a unit vector. So then the force vector, if you know the magnitude and direction, then you can recover the force vector. So it would just be this. And I'm going to focus on just the z component of the force. And I'm also going to divide out the mass of the point mass. So this is kind of like the acceleration then. Right, so if I look at just the z component, then it would be this. And if we divide out m, here we have that. Now to keep things simple, let's say we've got a certain amount of material and we're stuck with that much volume of material. And it's going to be of a constant density to keep things fair. So let's say, well, if we took whatever amount of material we had and we put it in a sphere, let's use units of distance, so the radius of that sphere of all the mass that we have, units, so that r would be 1. And then we'll use units of mass, so that we'll call the entire mass 4/3 pi. Right, so we'll choose the units of distance and mass to be that. And then this would mean the density is 1, right? So, and then we can choose units of time, so that g, the gravitational constant, is 1. So if we do that, calculations will be easier. So then the gravitational pull from a mass somewhere is given by this, as we said. And let's say I have some shape. This one looks a lot like a sphere, but it could be whatever shape. We've got all sorts of infinitesimal masses everywhere. The total z component of the force from all those masses would require a triple integral of the solid, of the z component of each dm there. And again, this is with the point mass at the origin, and then the solid I'm going to put with negative z's, so that my point mass is kind of going to end up being at the north pole of the shapes I look at. Just to mention, if I want to generalize and put the point mass anywhere, say at the point ABC, and I use this version of gravitational force with a minus, well, that's when r is from the big mass towards the point mass. So we have that minus. Anyway, so that would be the direction. And so we get a similar formula, but so we could have the point mass anywhere in 3 space. Mu is basically the density times dV for the amount of mass m at somewhere in 3 space. So we get kind of a similar triple integral. Again, for us, the point mass is at the origin. Well, we might as well look at a sphere first. I'll put it radius 1, but centered at 0, 0, -1. And if you multiply it out, you can put it in spherical coordinates. Rho is -2 cosine phi. We'll describe this. And if I want positive rho, radius, I'll use angles from pi/2 to pi. So if you know your spherical coordinates. So this would describe the sphere. And we'll just double check the volume integral. 1 dv will be rho squared sine phi d rho d phi d theta, where rho goes from 0 to the equation of the sphere for angles of phi pi over 2 to pi and theta 0 to 2 pi. Do the theta integral first. This is going to be rho cubed over 3, plug in my limits, and then you can integrate cosine cubed sine. If u is say negative cosine, then you just get du sine. Anyway, so you get cosine to the 4th, and we get, of course, 4 pi over 3. For the force of gravity, it's those same limits, but this will be our integrand instead of 1. And in spherical coordinates, it'll be rho cosine phi is z. I did the theta integral already, 2 pi. And now again, I can integrate cosine squared sine. It'll be cosine cubed over 3, absorbs that minus. And we actually get, so negative 4 pi over 3. So it's just like all the mass, which is 4 pi over 3, is 1 unit away, or in other words, at the center, which would be at 0, 0, negative 1. And of course, that's a well-known result. For spheres, you can always treat the mass as if it's always at the center, as long as your density is radially symmetric. For the next shape, if I look at a rectangular box, this one's kind of easy to set up. So we want the volume to be 4/3 pi. So I'll have it so I go negative a to a, well, this way for x and y. So that's 2a by 2a. Then the height will be from 0 to b, or actually I'll put it under, so it'll actually be from negative b to 0. So this is what I need for the volume to be 4/3 pi. And so this integral will just be this way. And through experimentation, I found I got a maximum at about a is about 0.827, b 1.531, so it's almost like a cube, and then g is negative 4.19, or in other words, this actually has more pull than a sphere. So here's not the shape. This shape goes from negative 1 to 1, so this is a 2 by 2 by pi over 3. Again, if you put something at the North Pole there, what would the pull be? Well, first I'll find the volume, 4/3 pi, and that's about 4.1888 if I round. So that would be the volume, and again, that's the pull for the sphere. But if I do the triple integral here, well, actually, let me make a equal to 1 first. So I got negative 3.97, so it's not as strong. So this is with the point mass at the origin. So again, a negative 3.97. And again, it was about at 0.827. You'll just have to trust me. At least to 3 decimal places. This gave the maximum pull in the downward direction. So actually just slightly more than negative 4.19. Slightly more in magnitude. The picture, it's more like a cube. Right, so x and y, these are those range. So about 1.654. The height, about 1.53. For a cylinder, again, if I want the volume to be 1, the volume of a cylinder is pi r squared times the height. So I need, if I call the radius a, I need a squared times b to be 4/3 to get 4/3 pi for the volume. So then this triple integral will be, for r, I'll go 0 to a. For the height, I'll go negative 4 over 3a squared to 0, and then theta 0 to 2 pi. And this integral's doable. I won't show all the details, but there's where the max occurs roughly. And so now there's even a bigger pull downwards, so more than the negative 4.19, it's more like negative 4.22. Here's a plot of the downward pull as a function of a, and you can see there's a maximum very close to 1, but it's actually a little less than 1. I took the derivative, and maple, put it equal to 0, and it was at that 0.9332. So this would be the radius and the height. The shape would look something like this. So put something there at the North Pole. That's the shape that'll give you the max pull of all cylinders of fixed volumes 4/3 pi. For ellipsoids, that'll be kind of symmetric with respect to the z-axis, kind of like that, but then I shifted it down one. It doesn't really matter, the math's just as easy one way or the other, or just as hard. But again, for the volume, it's 4/3 pi times this product, so it'll be a squared b. So again, I need a squared b to be 1, or b to be 1 over a squared. So I'm going to have a kind of a circular radius of a, but then a different value here. So this ellipsoid has horizontal slices will be circles. So again, if I put this in cylindrical coordinates, that'll be r squared over a squared. So the center is at 0, 0, negative 1 over a squared. That's the b. And then b squared. So if I solve for r squared, I did it in many ways for different purposes. But so that's my limit of integration if I integrate r first. So r will go from 0 to the surface for all the values of z from negative 2 over a squared to 0, right? The center is at negative 1 over a squared. Just b below the origin. And this integral didn't evaluate to elementary functions, so I left it like this, and through enough trial and error, this would be the maximum. So now it's, again, a stronger pull, negative 4.28. So negative 4.1888 for the sphere, negative 4.19 for the rectangular box, negative 4.21, I think, for the cylinders, and now negative 4.28 for the best ellipsoids. Here's a picture of that ellipsoid, kind of flattened. If I plot the graph of that integral times 2 pi, again, now the maximum occurs a little beyond 1, and through a lot of testing, this was the maximum there, 1.116, and even 1.1161 and 1159 were smaller if you compare. But anyway, so that was the best value to 3 decimal places. So how do we find the best pull? Is that the best possible? It seems, it's nice and symmetric. It's kind of just like a adjusted sphere. But the way to find the max pull, because we can do better, is go back to the equation for, the G felt is given by this equation. And if your mass is below the xy plane, then the z component will be in the downward direction. So it'll equal some negative number. Now, if I find all the points where it's the same negative number, I get the graph of a surface. And for each value of k, you're going to get a family of surfaces. And then there's one value of k. It ends up being a closed surface. I guess we can't tell that right away yet, but you get a closed surface, and the value of k being 1 over 5 to the 2/3 is the value, so that the surface will have volume 4/3 pi. But anyway, so we're going to set where the force of gravity is equal to a constant. So first let's look at the plot. And again, I'll do it in spherical coordinates. So z is rho cosine phi. X squared plus y squared plus z squared is rho squared to the 3/2 will be rho cubed. I want that to equal negative k. We can cross multiply and then square both sides. If I divide out rho squared, I'm down to this. And I want to take the square root of both sides. So rho squared can be plus or minus. Now, rho squared can't be negative, but we're actually going to use values of phi from pi over 2 to pi, which means cosine will be negative. So I actually need the negative cosine of phi. So rho squared will be negative cosine of phi divided by k. And then this will be positive for these values of phi. So now I can take the square root. And then I just change 1 over root k to the value of c. And so I'll first find the value of c so that the volume is 4/3 pi. Okay, we might not even know we're looking at a closed surface yet, but we are. So it's not too hard. Just triple integral of 1. So if I put my limits, it'll be 0 to 2 pi for theta, pi over 2 to pi for phi, then 0 to c square root of negative cosine phi for rho. 1 dv will be 1 rho squared sine phi. And I can do the theta integral again. That'll be 2 pi. The rho integral will be rho cubed over 3. Plug in my limit, I'll get c cubed, and then this quantity to the 3/2. Right, rho cubed over 3, so it'll be this, then still times the sine theta. So now we can do the phi integral. Just let u equal negative cosine phi. Du will be sine phi. And I'll get u to the 5/2 divided by 5/2 or times 2/5. So it'll be, this will be the antiderivative. Plug in my limits, plug in pi. I'll get negative of negative 1, which will be 1. And plug in pi over 2, you get 0. So you just get 2/5 times that. So 4/15 pi c cubed. And again, so if you want the volume to be 4/3 pi, c cubed would be 5. C would be 5 to the 1/3. So 1 over root k is 5 to the 1/3, or k is 1 over 5 to the 2/3. So let's look at the plot. So here's the sphere. Rho equals negative 2 cosine phi, or 2 times negative cosine phi. So that's the sphere that's below the xy plane. Radius 1, diameter 2, centered at 0, 0, negative 1. So here's the surface. If I plot it implicitly, it looks like this. So kind of tell it's closed. It's not the best way to plot. If you can do it in spherical coordinates, it'll look a lot better. But this isn't too bad. If I square both sides of that above equation, I get a top half as well. Of course, we're not worried about that. Here's both parts in spherical coordinates again. So I have phi going from 0 to pi. I only want phi to go from pi over 2 to pi. So there's the 0 to pi over 2 part. This is the pi over 2 to pi part. So again, this will have volume 4/3 pi, and that's the shape. So it has maximum pull. So now we see it's closed, and at every point on the surface, the gravitational pull is the same. Right? So any point you pick on the surface, if I look at the z component of the pull from that point to a point mass at the origin, it's the same no matter where I choose on this surface. So let's deform that surface, and I'll deform it, say, into a sphere. So this is the sphere again, unit sphere. And so we can see through both. Here's the surface with the max pull. So if I look at them both together, it looks like this. So here's the max pull in blue. So if I change the shape of this max pull in blue surface, if I change it, then essentially what I'm doing is taking mass from inside of the surface and moving it to the outside. But mass inside will have a stronger pull. It's going to be closer to the origin. And if you move it to the outside, you're moving it outside this surface. The z component of the force would be weaker. So any deformation of this surface, which has a constant pull, that's how we solve for it, means that you essentially took mass from inside, where the pull would have been stronger and moved it to the outside where the pull will be weaker. So that's how we know this shape will have the max pull. All right, so to compute the pull, we'll integrate z, which is rho cosine phi, divided by x squared plus y squared plus z squared to the 3/2 times 1 dv. So here it is in spherical. The same limits as we just had, except now I know what the c is, 5 to the 1/3. So again, we can do the theta integral first, get 2 pi. If I look at the rho, I'll get rho cubed over rho cubed. That'll cancel. So the antiderivative of the constant will just be rho. Plug in the limit, upper limit that, plug in 0, 0. So this will be our new integrand. Now to integrate this, it's a little tricky. I've got, because cosine is negative, and I have the square root of negative cosine phi. So I'll think of this as negative of negative cosine. And then I'll pull this negative out along with the 5 to the 1/3. So now I have negative cosine to the 3/2 times sine. And now u is negative cosine, du is sine. So I just get this to the 5/2 divided by 5/2. Plug in my limits. Pi, this will be negative of negative 1. Pi over 2 will be 0. So here we go. And, well, we did get a bigger value, and it's the biggest value possible. So I can't get larger than that for any shape. Right, so once I have a fixed volume of material of constant density, this is the shape. So there's the shape. Yeah, pretty kind of flat at the top, etc. All right, so now you know, and given any solid in 3 space, if you want to know what the pull is of that solid, maybe it's a floating cone or some other oddball shape. But if you can describe the shape and you know where you are, you can find the pull from the force of gravity that that shape will have on you. Note, finding the center of mass doesn't do any good except for the sphere. Although it's not too hard to show that the farther you are away from the solid, the more it looks like all the mass is at the center of mass. So for all shapes except for a sphere, you can't put all the mass at the center and get what the gravitational pull will be. You actually have to do the triple integral. But the farther away you are, the less that matters. All right, so time to wrap up. Hope you enjoyed this as much as I did. Anyway, thanks for watching and have a good day.